Hello everyone, this is lecture 2.2, which is focused on open methods, which is, one of the ways that we find roots in numerical methods. So we've already covered bracketing methods, the bisection and the false position method. Today we're going to look at open methods. More specifically, we're going to look at fixed point iteration and Newton Raphson. All right, so this is part of chapter 6 in the textbook, Roots of Equations. So open methods, single starting point or two starting points, not necessarily to bracket the roots. So before, we had to bracket the root. In the open methods, we don't have to bracket the roots in the initial kind of starting point that we're, which is basically the initial guess. So here we have two implementations of the Newton Raphson method, and you can kind of see, unlike the bracketing methods, in the open methods, the method could diverge. So here A is an example where the method is converging, and B is an example where the method is diverging. So let me show you kind of more closely how does that look like. So this is our initial guess, xi. So this is where we guess the root is. And then this method uses the slope at this point here in a way where we can see it projects towards the x-axis. And this is the second guess. And then from that second guess, it goes back to the actual line. And then using the slope here, goes towards the real root. So in this method, we are converging. In B here, we diverge. We can see this is the initial guess, xi. It moves down to the line. We draw the line to the second guess. From here, we project it onto the function, and you can see that it's moving away from the root, which is over here. So in this case, B is diverging. So unlike the bracketing methods, open methods could diverge, which is a key important thing to take home in this case. All right, so the first method we're going to look at is a simple fixed point iteration. So in this method, given a function, f of x, we need to rearrange this function to isolate a single x to one side. So for example, if I have a function like this, and our goal is to get the function equal to 0, so we're trying to find the 0 here. So we're only going to have the x's, or f of x equals 0, and whatever's on the other side present in the equation. We rearrange it in the form so we get 1x on one side, and then on the other side we have whatever is left in the function. In this case, we're going to call it g of x. When we have this format, then we can iterate. So what we do is we sub in our initial guess into the function gx. Whatever we get will be the resulting estimate of the root, which is xi plus 1. So we do this several times until hopefully you converge to an actual root. So we're going to do an example now to show you guys how is a simple fixed point method or iteration method applied to a specific equation. All right, so this is where we're going to be doing the example. So this is from slide 5, and this is the simple fixed point iteration example, and this is slide 5, obviously in lecture 2.2. So we're going to use the fixed point iteration method to find the root of the following function. So f of x equals 0 equals x squared minus x minus 1. So this is the function. We have 0 on one side, so that's great. So now our goal is to rearrange this equation to get, if you remember, right, x equals g of x, and then we need to iterate that. So we need to isolate x to one side, and we have many options to do this. So we're going to try multiple options and show you what happens. So in option 1, we're going to have move the x squared, basically isolated to one side, equals to x plus 1. And then we're going to divide by x on both sides of this, this expression here to get x equals 1 plus 1 divided by x. So now we can iterate this function here. So the iteration form is going to look like this. xi plus 1 is going to equal to 1 plus 1 divided by xi, where xi is our initial guess, or whatever kind of approximation we have in whatever previous iteration that we have. So to start, let's use an initial guess, x naught, which is equal to 2. So this is our initial guess. All right, so that's x naught. So if we're doing an iteration, right, in the first iteration, we're going to be looking at x, naught plus 1. So therefore, x naught plus 1 is basically x1 equals to 1 plus 1 over xi, or sorry, x naught in this case. So let's just say here I equals 0. All right, so that I plus 1 is equal to 1. That's why I have a 1 here, and then that's why we would have, x naught here. And x naught in this case is the initial guess. So equals 1 plus 1 divided by 2. So this is equal to 1.5. Now the percent relative error in this case would be basically what's 1.5 compared to the initial guess, which is 2. So I can write as an initial approximation of the percent relative error is equal to the absolute value of 1.5 minus 2 divided by 1.5, again, absolute times 100%. So if you do this math, you would get 33.33%. All right, so then now we do the second iteration. Now we can say I equals 1, right? So then I plus 1 is 2. So x2 is equal to 1 plus 1 over x1 equals 1 plus 1 divided by 1.5. Here we get 5 over 3, or approximately, if we look at decimal places, 1.67. Again, we can calculate the percent relative error in this case, and we find that it's 10%. We do it again, right? I equals 2 in this case, so x3 equals 1 plus 1 over x2 in this case, which is 5 over 3. You do the math, and you get 1.6. Relative error, in this case, 4.167%. You can keep going, right? Go up to like x10, and you would get about 1.618 with a relative error of 0.005%. So here we can see clearly that the percent relative error is decreasing every step approaching 0. So in this case, we can clearly say, right, that this method is in fact converging. at least in the conditions that we're using it in. So again, we rearrange the function that we were starting off with right here into, up here, into isolating x to what we see here, and then we performed the iterations and got that result. So now we can try, what happens if we didn't arrange it in that way and in some other way. So option 2, as an example, we have, x squared equals x plus 1. So if instead of dividing by x, we actually just took the square root of both sides, we would end up with, x equals plus or minus square root of x plus 1. In this case, when we're trying to iterate every time, right, we're going to have xi plus 1 equal to plus or minus square root of xi plus 1. Would this be useful? Not really, because every time, we try to iterate, we have two options. So not the best approach. So two options, not the best approach. All right, so let's look at another option. In this case, option 3. And then we have x squared equals x plus 1. And we rearrange it so that we have x squared minus x equals 1. And then we factor out an x. So we have x minus 1 equals 1. And then in here we have x equals 1 divided by x minus 1. So in this case, we would iterate the function xi plus 1 equals 1 over xi minus 1. So again, starting with the same kind of initial guess that we had before, right? X naught equals 2. This would result in x1 equals to 1 divided by 2 minus 1. This would give us basically 1 divided by 1, which is 1. In here, looking at, the relative change or percent relative error, in this case is 100%, because we went from 2 to 1. x2 would be what? 1 divided by 1 minus 1. You would get 1 over 0, which is what, in this case, basically infinity. So that we can't really continue with. So then, technically, we could put in, 1 divided by infinity minus 1, and then end up with a 0, right? And then continue from there. Another option to do is we can just say, all right, let's just change the initial guess. Let's just say x naught instead is 1.6. And then redo. So x1 is equal to 1 divided by 1.6 minus 1. This will give us 1.67, which is, relative error equal to 4%. Then we can have, this is also the same as 5 over 3. So x2 can be, in this case, 1 divided by 5 over 3 minus 1 equals to 1.5. Percent relative error, do the math, you get 11.11%. x3, we keep going, is going to equal to 2. x4 is going to equal to 1. And we can see that the relative, the percent relative error in this case is actually increasing instead of decreasing. And this goes back, right, where x5 actually is infinity again. And x6, like I said before, would be 0. And then x7 would be -1. And then you keep basically going. If you keep going with this, you would get that x17 is -0.61806. And after that, it kind of converges into this value, which in fact is a root, but not the positive root of this function that we're trying to solve. So let's note here. So if we kept going, as we see here, converges to another root, which is what we see here on the negative side. So then essentially what we can say here, we had initial divergence. So initially it's diverging. But then after that, somehow it converged into, another root, which, it depends on the goal of the problem. Sometimes, having a negative root does not make sense in your engineering problem. So in a sense, you don't really want that value. But in another, problem, it could be that you are looking for a negative root, but in that case, you probably don't want to start with a positive guess for your root. So again, it depends on the problem, but this is an example that clearly kind of shows you how the fixed point iteration method can be used, and essentially how once you use it, you can sometimes converge and sometimes diverge. So here we have in the slides. So going back to the slides, we can kind of see these two options that we kind of tested out with this fixed point iteration method with an initial guess of 2 and 1.6 for these two different arrangements, and how the estimated root, right? So here on the y-axis we have the estimated root, and on the x-axis we have the number of iterations. So from the first iteration, in blue here, blue is option A and red is option B. Blue, we started with 2, and then you can see from 2 drop down here, and then basically converge to this value, which is 1.61803. That's the positive root for this function. In terms of B, option B here, instead of converging to this positive root, instead, it kind of jumped around, went back to 0 from after infinity, and then, -1, and then converged to this negative 0.61803. So two different results from this method that we can see here. So here we see the relative errors. So in blue for option A, we can see that, it's a gradual decrease, and kind of we can clearly see this is a nice curve showing convergence. And then in red here, we can clearly see, a very typical curve for divergence where it's not approaching 0, the relative error. It's just increasing and going into infinity. But like we said, eventually, the percent relative error does go back to 0 when it converges to the negative root for option B. Here we see the actual graph, right, for the function that we were analyzing, which is x squared minus x minus 1. So this is the curve of that function. The 0 right here, this is the 0, is highlighting the roots. So this is the one root and this is the other root. And here we see the different points, right, of where we had the initial guess of 2, and from there, the other kind of estimates of the root shown on this graph until it converges to the positive root that we see here. And then for the second option B, where we initially started off, in the positive side, and then eventually what it did is it went to the negative side. So on the x-axis, this is the positive side, and then this is the negative side, and it basically converged to a value which is the negative root of the function that we were testing out using this method. So again, just some graphs to kind of show you what's happening as we iterate from step to step while we're trying to find the root of the function using this open method, which is called fixed point iteration. So here we see the true relative or true percent relative error in this case, when the goal is here in this case to find the positive root. So we can see option A converges, option B diverges when we're considering that the true value is the positive root. So here we see this kind of characteristic plot for the fixed point iteration method. And it's basically saying that this method experiences linear convergence. And what we're looking at here is the fractional change in the true percent relative error. So this is the true percent relative error at point I divided by the true percent relative error in the previous estimate. So as we approach the true value, we're basically the true percent relative error kind of becomes more kind of following an exact kind of multiple in a linear fashion, getting to that result. So again, just a characteristic plot for this method. It kind of shows how fast this method would basically converge if it was working well. And we will compare this kind of characteristic plot to another method and see how that one looks, which is the Newton Raphson method, which we're going to cover next. All right, another thing to mention here is if we're looking at this method, if we plot, the left side of the equation versus the right side of the equation, right? When we're doing the fixed point iteration method, we're isolating x on one side, and then whatever's left is on the other side. So if we made these as two different functions and we plotted them, we can kind of see where the root is in this function, which is located right at the intersection between these two kind of functions, right? Because when x is giving us a value which is equal to the root, then both sides are gonna have to be kind of the negatives of each other, and then when we put them together, it would give us f of x equals 0. So this is the root, we see that clearly, and we're going to use this to kind of analyze when does this method converge versus diverge. So there's a kind of characteristic by looking at the y equals x graph versus the y equals gx graph. 4 different examples here presented. So essentially what is observed is that if the derivative, the absolute derivative of g of x is less than 1, then the method will converge. If it's not less than 1, then it will not converge. So let's see how this looks like in a graph. So here we have an initial point x0. We have a point here, right? This point here on the y. And we can see that the slope of this point is less than 1 because the slope is 1 when y equals x, right? So if I'm looking at, let's draw this out here. If I'm looking at this point versus this point, right, the slope here is 1. The slope here is slightly less than 1. Anyway, so what happens here is this method will guess that this is the next guess for the root. And then we can see that the slope here again is less than 1. Then it goes again, makes another guess, right? And again, we can see here the slope is less than 1. And this method basically is converging. So, and g prime of x, which is the slope of g of x, absolute, is less than 1 with all these kind of x values. Clearly from the graph. So we're not doing any math, we're just looking at the graph. For the b graph here, we have an initial guess x naught here, and this is the value. And we can see again that the slope here is less than 1. From this, the fixed point iteration method will guess that this next point, is the next kind of guess, x1, and you can see, sorry, you're right. And it goes to here, then goes to here, and then goes to here. And essentially, eventually gets to the root, which is in the center. And as we go from point to point, the slope is always less than 1. So again, this is a case where it converges. So A and B both converge. Let's look at these other options on the bottom. So here we have x naught, and this is kind of the g of x line right here. And you can clearly see now that the slope right here at this point is much greater than, a diagonal line. This is the diagonal line, right? Much greater than the diagonal line. So therefore, g prime of x absolute is greater than 1 in this case. And we can clearly see that, the next guess here is moving away from the root, which is over here, right? You can see that again and again, right? This would be, x1, this would be x2, and so on. So this method is diverging. Similarly, this method, we can see that the line here, g of x, also has a very high slope, and the same thing happens. So in a way, when you're rearranging an equation, one way to check if your method will converge or diverge for this open method is to check the absolute, basically derivative of the function g of x. So when we wanted to check the functions that we used in the example earlier, g of x for the first one, option A, is 1 plus 1 over x. The derivative in this case is negative 1 divided by x squared. If we plug in the initial guess, 2, we get negative 1 divided by 2 squared, absolute, which is 0.25. This is less than 1, and in fact, this method did converge. Option B, 1 over x minus 1. Derivative of this is negative 1 over x minus 1 squared. We plug in the initial guess of 2, we get a value of 1. And this method, in fact, did diverge, at least from the root, the positive root that we were trying to find. So again, just a way to gauge if our open method fixed point iteration would converge or diverge. All right, so now we're going to move on to the Newton Raphson method. And this is basically based on the Taylor series. So if you recall from the first lecture, Taylor series f of xi plus 1 equals f of xi plus the derivative of f prime xi times the step size, which in this case is xi plus 1 minus xi. So when we're trying to find the root, we're going to be basically trying to find when f of xi plus 1 equals 0. So in this method, what they do to derive the equation is basically to say, all right, let's make this equal to 0, and then rearrange the function to solve for what would xi plus 1 be given an initial guess for xi. So this is the Newton Raphson method equation, which is derived from the Taylor series. So again, we saw kind of an example in the first couple slides, but we will go kind of deeper into this in also an example later on. So here we have our initial guess xi. We draw a line, or kind of, this is the function here. The blue line is the function. And what we're doing is we're looking at the slope, right? where does the slope at that point intercept with the x-axis? And this would be that second guess after that. And then you draw a line again, draw a slope, and then that would be your guess. Then draw a line, get a slope, and then eventually, obviously in this method, it will converge on this plot that we see. So if we look at kind of the same problem that we had in the previous lectures, x squared minus x minus 1, and we tried out the Newton Raphson method, we would see that, if you remember that characteristic plot where the fixed point iteration method had a linear convergence, well, in the Newton Raphson method, it's a quadratic convergence, meaning that it's much quicker in converging. So if, for example, right, we had the true percent relative error of my current kind of I is 0.15, then the step forward, so true percent relative error for I plus 1 would be proportional to 0.15 squared, which is 0.0225. So again, for when we're basically analyzing how fast does this method converge, well, it's pretty quick compared to the fixed point iteration method. So again, both the methods we've covered in this lecture so far are open methods requiring a single initial guess. So here we see kind of the true relative error for the Newton Raphson method compared with the fixed point iteration method. And you can see that, it took 1, 2, 3, iterations, and we're kind of almost at 0. While the fixed point iteration method, we had, 1, 2, 3, 4, 5, and we're still not even near that 0, right? And 6, 7, maybe at 7, we've approached that 0 point. So again, just highlighting that the Newton Raphson method is quicker than the fixed point iteration method in finding the roots. All right, so one thing to note here, though, is Newton Raphson, is not immune from diverging. So we can see here some examples where it diverges. Imagine we had this type of function, and we had an initial guess x0 here, draw a slope, x1 here, draw a slope, x2 here, draw a slope, and it's gone away from the root, which is right here. Here we can also see another example, our initial guess for the root. So again, the root is right here. We draw a line, see the slope goes this way. Again, another line with a slope going that way. Another line, slope going this way. Another line to x4. Another line out of the chart. So 2 examples where the Newton Raphson method would actually diverge in this case. Here we see some more examples, again, diverging away from any of the roots that we see here. And in this case, x0 also going to a really far value, way down, far away from your initial guess. All right, so now we have a practice problem using the Newton Raphson method, which is estimating the root of the function e to the power of negative x minus x, employing an initial guess of x0 equals 0 with 6 significant figures. How many iterations did you need to find the root of this function? All right, so let's try this out. All right, so this is the practice problem. And we have the function f of x equals e to the negative x minus x with an initial guess of x0 equals 0. And we want to get at least 6 significant figures which are accurate. So if you recall, right, how do we get this? We're going to have to apply kind of the tolerance equation that estimates what relative error, right, percent relative error, will I get 6 significant figures? and that equation is 0.5 times 10 to the power of 2 minus n, where n is that number of significant figures. So if we plug in for n, 6, so 2 minus 6, we will get a value of 5.0 times 10 to the negative 5%. So quite a small number. All right, to apply the Newton Raphson method, if you recall, the basic equation, we have xi plus 1 is equal to xi minus f of xi divided by f prime xi. So in this case, we're going to need the derivative of this function. So f prime x is negative e to the negative x minus 1. So generally in this course, I'm not going to give you, derivatives that are very, very hard to find, just to make sure that everyone is able to do the problems without having difficulty to basically find the derivative. All right, so let's do the first iteration now of this method, and we can apply the equation that we see here. So x1 is going to equal to the initial guess, which is x naught, which is in this case 0, minus f of xi, which in this case is the initial guess, so f at 0, divided by f prime at 0 also. So I'm not going to do all the, the simple calculations. So to get f of 0, you basically plug in 0 to this equation, and then f prime at 0, you plug in 0 into this equation, and you get the values. So you would get 0 minus 1 divided by negative 2, which is 0.5. So here we have, a percent relative error of 100%. That's going from basically 0 to 0.5. Then we're going to go to the next point. So this will be our second iteration. And obviously, this is not less than the tolerance which we're going for here. So we're going to go and do another iteration. So x2 is going to equal to 0.5, which is our, x1. Let's try this 5 again. Minus f at 0.5 divided by f prime at 0.5. Do the math, you get 0.566311003. All right, you do the math, you get a percent relative error of 11.709%. And, for practice sake, I expect you guys to, try out these calculations just to make sure you always remember how to do those for a quiz. x3 equals, this large number, 0.56311, minus the function f at 0.5666311, divided by f prime 0.5666311. Do the math, you get 0.567143165. All right, and here, percent relative error now is down to 0.1467%. So we are obviously converging and getting closer to that goal of 5 times 10 to the negative 5 with 6 significant figures that are basically exact. So x4, we apply the same equation. And here I'm just going to write x3 minus f of x3 divided by f prime x3 instead of rewriting that entire value. Do the math, you get 0.567143290, with a relative error, percent relative error of 2.204 times 10 to the negative 5%. So is that lower? Yes, it is. So this is 5 times 10 to the negative 5. This is 2.2 times 10 to the negative 5. Therefore, we have reached our goal of the absolute percent relative error being less than the tolerance. Therefore, it requires 4 iterations using the Newton Raphson method to get 6 significant figures which are accurate. So therefore, 4 iterations are required to achieve 6 significant figures that are accurate. All right. So here I have a slide where, we could basically see what we did in kind of that drawboard software, where we took out this function, found the derivative, used the initial guess, and going from one iteration to the next, we found the values where we achieved basically 6 significant figures, which is what we see here, that don't change between the third and the fourth iterations, giving us that tolerance, less than that tolerance value for the percent relative error. All right, so that brings this lecture to an end. We've covered 2 open methods, the Newton Raphson method and the fixed point iteration method. And in the next lecture, we will cover the 2 other open methods in this course. Thank you for listening.